Students, welcome to s.mathguru classes. So our main discussion is formation of partial differential equation by eliminating arbitrary constants and by eliminating arbitrary function. Now arbitrary constant two videos it was given. Now we consider how to solve form partial differential equation by eliminating arbitrary function. Now let us consider one problem. Form the partial differential equation from z equal to f of x square minus y square. This problem is given. Now anyhow do or die, anyhow we have to remove f. Here z equal to given f of x square minus y square. This is our z. We differentiating partially both sides with respect to x. Del x f of x square minus y square. So we differentiate this. So del z del x means we know p, and this is f dash x square minus y square del x square minus y square. We get this x square minus y square. Now actually we know this formula ddx of fx then f dash x. We know this. When you get f dash x, if x same, then we get f dash x. But here x square minus y square. So using chain rule, we get this one. So this will be p f dash x square minus y square. This is twice x and minus 0. We differentiate partially with respect to x, then this is twice x and this one 0. So ultimately we get p twice x f dash x square minus y square. This is number 1 we consider. 1. Next again we differentiate this one with respect to y. Again del z del y del y f of x square minus y square. So del z del y means q, and this will be f dash x square minus y square del y x square minus y square. We get this, and this implies q equal to f dash x square minus y square. This is 0, this is minus twice y. We differentiate partially with respect to y, then x is constant, this is 0, and y square means twice y. So this implies q equal to minus twice y f dash x square minus y square. This is number 2 we consider. Now actually our aim is how to remove f, the function. Now 1 divided by 2, this implies 1 is p and 2 is, this is q, and on right hand side this is twice x f dash x square minus y square, this one, and this is minus twice y f dash x square minus y square. We get this p by q, this is minus x by y. This 2 will be cancelled, 2 also cancel, x by y, and cross multiplication yp minus xq. This is xq plus yp equal to 0. So in final result f is absent. So this is the required solution. Formation of partial differential equation by eliminating arbitrary function. So function is absent and this is the required solution of the given problem. This is the problem we consider. By means of a partial differential equation, eliminate the arbitrary function from the equation x plus y plus z equal to f of x square plus y square plus z square. From this, we want to construct a partial differential equation by eliminating the function f. Now, solution is start. Given that x plus y plus z equal to f of x square plus y square plus z square. First, we differentiating both sides with respect to x. Del x of y, del x of del x of x, del x of y, del x of z, and del x of f of x square plus y square plus z square. So del x is 1, this is 0, and del x is p. And this is if we write directly, then without showing the partial chain rule, x square f dash x square plus y square plus z square del x square plus y square plus z square, we get this one. This is 1 plus p equal to f dash x square plus y square plus z square twice x 0. This is twice z del x, this one, and this will be 1 plus p. From these two terms 2 is common, then f dash 2 into f dash x square plus y square plus z square x plus z into p. Del z del x p, 2 is common, we get this one. So by differentiating with respect to x partially, we get this is our relation. This number we consider 1. Now again we differentiating with respect to y. Again differentiating both sides with respect to y. Del y x, del y y, del y z. This is del y f of x square plus y square plus z square, and this is 0, this is 1, this is q, and if we write directly, this will be f dash x square plus y square plus z square del y x square plus y square plus z square. We get this, and this implies 1 plus q equal to, this is f dash x square plus y square plus z square, and we differentiate partially with respect to y. X is constant, this is 0, and y square del y, this is 2y, and z square means 2z del y. This implies 1 plus q, 2 common, f dash x square plus y square plus z square, and this is y plus z q. Del z del y means q. So we get this is number 2. We get 2. Now 1 divided by 2. So 1, this is 1 plus p. In left hand side of 1 plus p, and this is 1 plus q, and on right hand side of 1, this is 2 f dash x square plus y square plus z square into x plus zp divided by 2 f dash x square plus y square plus z square into y plus z cube. So our main target, how to remove the function. So if we divide, then function will be cancelled. These two terms will be cancelled, two factors, and we get 1 plus p, 1 plus q equal to x plus zp and y plus zq. We get this one. After cancelling, we get this. Now cross multiplication, this into this, and this is y plus q, x plus zp. We get this one. This implies first multiplying by y plus zq, next multiplying by py plus pqz, and on right hand side multiplying by 1 x plus zp, this is qx plus pqz. We get this. pqz cancel. So after cancelling, we get y plus zq plus py equal to x plus zp plus qx. We get this one. Now zq plus py minus zp minus qx equal to x minus y. This y taking on right hand side. Now from this, first taking p common, from these two p common, then y minus z p, this and this p common, and from these two q common, z minus x q equal to x minus y. So from these two terms, taking p common, y minus z into p, and q common from these two terms, z minus x equal to x minus y. And this is the final answer. How could we know this is final answer? Because our aim to remove the function. So function is removed. Here function is absent. The function is f is absent. We get a relation. This is the required solution of the equation. Now this is the required partial differential equation. Consider another problem. Eliminate the arbitrary functions f and small f and capital F from this relation y equal to f of x minus at plus f of capital F of x plus at. Now we have to eliminate small f and capital F. Given that y equal to f of x minus at, f of x plus at, this number 1 we consider. Now we differentiating partially with respect to x. Here x and t given. So del y del x. This is del x f of x minus at del x f of x plus at. So this implies del y del x. This is f dash x minus at del x minus at, and this is del, this will be capital F x plus f dash x plus at del x plus at. So this implies del y del x, this is f dash x minus at 1 minus 0 del x 1, and this is 0, f dash x plus at, and this is 1 plus 0. We get this del x 1, and this is constant 0. So ultimately we get del y del x equal to f dash x minus at and capital F dash x plus at. We get this. Now again we differentiate with respect to x. Again del x del y del x del x f dash x minus at del x capital F dash x plus at. This implies del square y del x square f double dash x minus at. If we differentiate dash, adding again another dash del x x minus at, and this is capital F double dash x plus at del x x plus at. So this implies del square y del x square equal to f double dash x minus at, this is 1 minus 0, del x 1 and this is 0, and here f double dash capital F double dash x plus at, this is 1 plus 0. Ultimately we get del square y del x square equal to f double dash x minus at capital F double dash x plus at. So this is number 2 we consider. So number 1 and 2 we consider. So first we differentiate with respect to x. Next another variable is t. We differentiate with respect to t. Again del y del t del t f of x minus at del t f of x plus at. We get this, and this implies del y del t f dash x minus at. So this is del t x minus at, this plus f dash x plus at del t x plus at, and this implies del y del t f dash x minus at, this is 0 minus a into 1. We differentiate partially with respect to t, x is 0 and this is a constant outside del t 1. And here also we get f double dash x plus at 0 plus a into 1. Ultimately we get del y del t, this is minus a f dash x minus at plus a capital F dash x plus at. We get this. So again we differentiate with respect to t, this one again del t del y del t minus a del t f of x minus at a del t f dash x plus at. So this implies del square y del t square equal to minus a, this is f dash double dash x minus at del t x minus at, and here a f double dash x plus at del del t x plus at. This implies del square y del t square. This is a f double dash x minus at into 0 minus a into 1 plus f double dash x plus at 0 plus a into 1. We get this. So ultimately we get del square y del t square minus minus plus a square f double dash x minus at, and here a is, here also we get 1a. So this is a, we have a, this is a square f capital F double dash x plus at, and this implies del square y del t square, a square is common, we get f double dash x minus at capital F double dash x plus at. Now our aim to remove f function. So this implies del square y del t square a square. This means from 2. This means del square y del x square. So this is del square y del x square. So we get this result from 2. So what we get, del square y del t square equal to a square del x square, and here both f and capital F both are absent. We get a relation. This is the required solution of the given equation, and this is the required solution or required equation. From this given relation we get this required equation, and this is the final answer. So I hope you are all enjoying with this problem solution. So if you are all enjoying, then please like this video, and if you are new in my channel, then please subscribe my channel and click the bell icon. Thank you.